so far we have been talking mainly about how to solve Schrodinger equation, the role of the potential energy function in the expression of the Schrodinger equation, and how it influences the problem from problem to problem, how as the V varies, how the nature of the solution of the Schrodinger equation changes. We'll be solving few problems very soon. We'll be solving actually 3 problems according to your syllabus. Apart from that, you have got chronic Penny model in the course of band theory courses. So that will be another application of Schrodinger equation. We'll do that, but let us for some time ask Mr. Schrodinger to take a bit of rest, okay? Because simply speaking, suppose you are solving Schrodinger equation and you have got a function psi, and I have been telling you every day psi is just a mathematical function, okay? Now suppose you get the function, and suppose it is sine function, cos function. To you, if you use the mathematical brain, it is just a function, mathematical function. Obviously, there are some constraints also. We will discuss. Not any arbitrary solution of Schrodinger equation is not going to represent the matter. There will be some condition. We will discuss that separately. But suppose you have solved the Schrodinger equation, you have got the wave function. Now the question is that what you do with the wave function? So for that purpose, what you do, you need some more information, some more knowledge. Okay, how to deal with the wave function psi. So to do that, I give some examples to you understand. Again, classical example. I cannot give you a quantum example in a normal daily life problem. Again, you see, I've got a ball in my hand. Okay. Now I've got a very simple question. Is that suppose I throw the ball like this? Okay, I throw the ball like this. Question is that what do you mean by the mechanics of the ball? Or suppose I throw the ball like this. Question is that what do you understand by the mechanics of the ball? Or suppose I throw the ball like this. What do you mean by the mechanics of the ball? Okay. The question is the first time when I was throwing the ball up. Okay, when I was throwing the ball up, it was moving in a straight line path. When I was throwing like this way, it was moving in a projectile path. And when I was moving like this, you may be telling that I am giving a small rotation to the journey of the ball. So now you may say this is projectile motion, this will be linear motion, this will be a rotational motion, like that. But common sense is that who told you that it is the basic concept of a linear motion, projectile motion, the word linear, the word projectile, word rotation, more are geometric concept. What you have been doing yourself so far to describe the motion? You see, to know whether it is moving in straight line or not, you have been doing this much. First you see the ball here, next you see the ball here, next you see the ball here. So what is your job? Your role is an observer. And what you have been doing with time, you are noting how its position is changing. Initially the position was here. So you note your time with the clock and the length of height from the floor, maybe the y1. Now it comes to y2, it comes to y3, like that much. So your job was the role of an observer in observing the positions of the chalk of this ball at various time. Okay, and that is the basics of mechanics. We describe the 2 questions, WH questions. That is where the object is at a given time. Now at the time maybe t1 it is at y1, at t2 it is at y2, at t3 it is at y3. And we conclude as with time the positions are changing, so it's a dynamics problem of motion. But question that is only position knowing is sufficient to describe the motion. Suppose I throw the ball again and I apply a force. Suppose the mass of the ball may be say 20 gram. So mass I am providing you, and I am applying a force maybe 500 dyne on the ball, and I wish to know where the ball will go after 2 seconds, or say maybe 5 seconds. So I am throwing the ball and asking you again where the ball will go after some time. Okay. Now you see, to answer this question, only position data is not going to help you. They can throughout you may say I will look at the ball for 5 seconds. That is good for 5 seconds. Suppose a train is moving, is leaving Kalyani station now. Okay, and I wish to know where the train will be after half an hour. Now, is it possible for you to run with the train for half an hour and keep on determining its position? Okay, it's not practical. So, which is more practical? Mr. Newton is there to help you. You use the Newtonian law, the amount of, I have given you some hints also. the mass of the ball, the force I am applying on the ball. So you have got Newton to help you. Force equal to mass into acceleration. Or if it is you may say for 1D problem, you may simply write down F is equal to m d2x dt2. Integrate it twice, you get the position at a given time. So life is easy the moment you take the help of Newtonian idea, okay? But what I am trying to emphasize, Newton's law everybody knows at your age. What I am trying to emphasize is that to describe the motion of the ball, you need some more data because you have to be predictive. You have to go for prediction where it would go after some time. You need more data apart from position and time. What is the force applied? What is the velocity? What is the momentum? All these data you need to know. So if you know all of them, you can successfully describe the motion of the object. Okay, now another option can take place. So only position and at a given time will tell you whether it is moving or not. But to do prediction where it will go after some time or so, you need more data. Okay, so position and time are primary information. You need some secondary data like force, velocity, acceleration, momentum, etc. Now another thing that can happen, you see what this ball can do. You see I am throwing the ball, you see what the ball is doing. Now the ball is actually colliding with the wall. Okay, it is colliding with the wall. Now for collision it may be elastic or it may be inelastic. For elastic collision, so when you see the single ball can move in a straight line path, in a projectile path, in a rotational path. Now to know the motion only, position and time are good enough. But to know where it would go after some time, that means you have to make some prediction, you need more data, like velocity, acceleration, momentum. And it means the same ball can collide also. To describe collision, you need more and more data, like kinetic energy, like potential energy, because for elastic collisions, the kinetic energy and potential energy, the total energy is conserved, and for every collision, momentum is conserved. So therefore, the single ball to describe, you need so many data. Okay, only position and time will tell you whether it is a problem of motion or not. But to get it done completely, it's how it is moving, where it will reach, whether it is colliding or not. So you need a lot of data. Now all of them, what they are doing, their single job is to describe the motion of an object that is called a ball. Now all these variables are describing the dynamics of a ball, so that's why these are called dynamical variables. Now the point is that for a ball, it's a big object, you can measure it easily. Okay, because you can see the ball, so what its separation from the floor, you can measure it. Okay, where it is going after some, you can measure it because you can see the ball, it's a big object. Problem is that in my class I do not discuss about balls, I talk about electrons, a tiny microscopic object. And to us, electron is manifested by a function psi. So again you have to rely on our mathematics approach. How from psi you can get this information. Okay, so let us get it in the mathematical way.
Hello, very good morning and welcome to class 5 of my course on quantum mechanics 2. It is indeed has been a very good journey so far. I have taken 4 wonderful classes of you. Up to class 1 and 2 was a mere discussion, introduction of whatever I did in the first year quantum mechanics 1 courses. So our main topic actually began from class 3, okay, where I talked about the probability interpretation, and particularly in the last class we talked about the ideas of how to get the wave function, okay, in a real physical problem, and also how to get this wave function in a real physical problem. The mantra is very simple, that wave function is a mathematical function. You use your common sense of mathematics to get the wave function. That is, you solve a differential equation, popularly known as the Schrodinger equation, and that is going to give you the route of penetrating into the quantum world. You solve Schrodinger equation, you get a wave function, and you stay in quantum mechanics. You do whatever you like. But before I begin this class also, I have taken one resolution that every day at the beginning of the class I will remind you some very basic issues, so that you never lose the continuity. Okay, what was going on, okay, what we are actually discussing in these classes, that continuity is always mentioned. First point that you should never forget, every day I will tell you, is this idea that this basic concept in a quantum mechanics class, my focus is on the wavy nature of the matter. Four things can happen in nature. A matter can show the property of matter. The example is collision of matters. Normal mechanics, Newtonian mechanics or Hamiltonian or Lagrangian, all classical mechanics to describe that object. And you mainly know Newtonian idea. And the proper wave showing the property of the wave, that is interference, superposition experiment, diffraction, something you did in first year classes. The wave showing the particle property, the Compton and photoelectric effect, which I have told you in the earlier classes. But all these are three are known aspects, but our focus is on the last aspect, the matter showing the wave nature. So this is something I will tell you every day. I will tell you because this is something of area of importance. You will only focus on this issue because this is uncanny, you do not know. That's why you are focusing on this. The physics of the matter when it is showing the wave property. And this is not story, it has been proved by Davison and German and all these things you know. And this wave of electron is not like classical way of thinking of the wave. In any case, wave means disturbance, fluctuation, variation, vibration, but it is not like light and sound. The wave nature of the matter in quantum mechanics is basically wave of probabilities. You can see again, this is a very old picture. In the last 2 days also showing you, if electrons are orbiting around, they are too tiny to be located by our naked eyes. So what we do, take chance to find out the electron. At a given point, chance will vary because electron is moving very quickly, as you can see in that bottom picture here, that this arrowheads, okay, just a second, these arrowheads, they are actually changing. These are all changing at a given point. This is becoming plus, minus, these arrowheads, okay, they are indicating they're becoming plus, minus, etc. So what does it tell? That a given point, something is varying, something is fluctuating, and that something makes a wave, and that is a wave of chances, wave of probabilities, okay, wave of finding the particle, okay, a probability of finding the particle. So with all these things, concept in mind, at the same time we have taken up, these are the few very typical examples I have been showing you. If a matter is moving, and again the common sense, I cannot take chance to find out the matter, chances are varying, that defines the wave. But I have actually twisted my word a bit after that, following the basic physical concept. If that is the waving part is the probability, it has to be always positive, but the curves are saying they can be both plus and minus. So to take care of that issue, we consider the waving part is any arbitrary mathematical function, not arbitrary, okay, there are some conditions just to obey, but it is just it's a mathematical function called a function, and represented popularly by the symbol psi. And more physically meaningful data is given not by psi, rather by psi square. Psi is just a function. If it is zero, there is no matter. If it is non-zero, there might be a particle or matter, and its square modulus gives the chance of finding the object, or probability of finding the object at a given point space, at a given point x at a given time t. That's the Born's idea, and total probability is always 1. Okay, that concept I have been sharing you. So that therefore it becomes very essential that in a given physical problem, your primary job is to describe the matter with this new way of thinking. It describe the matter in terms of probability interpretation. That is, describe the matter with first you get the psi of the matter, or a function of the matter, then you take psi square. So the first job that you have to do in any atomic level problem, any microscopic problem, any electronic journey now, is to find out the psi first. And the technique of getting psi, I told you, because psi is a function, you rely on a mathematics brain, how you get functions in mathematics. We get functions in mathematics very simply by solving a differential equation. So you will be solving a differential equation, and that equation was proposed by Erwin Schrödinger long back in 1926, popularly known as the Schrödinger equation. Just like in classical physics, my equation of motion is Newtonian idea. In quantum mechanics, my equation of motion is a Schrödinger idea. It's a second order, first degree differential equation, and I have discussed a lot about this equation in the last lecture. And this is the form of the equation. It's a second order first degree differential equation where h cut means Planck constant by 2 pi, a means the particle mass, b means the potential energy. I told you last day also, from problem to problem v is going to vary, and that will, depending on that nature of my solution, nature of my problem is going to vary, and I is root over minus 1. So these are the very common terms. So after that I told you, but specifically in the last class, that how v comes to a problem. Okay, this issue, that if it is zero, it will be zero if no force acts on the body. That is a case of free particle. It will be non-zero. That is more realistic of case actually. Suppose an electron is moving under Coulombic force in an atom, then, and in all those situations, the attraction, the force and the particle, external force on the object under motion will be other than zero. Then you have to consider a non-zero v. You have to calculate it, and you have to solve that in a real physical problem. That will be your job. That depends on the problem. We will be solving problem. There we will take up the situation one by one, how v is going to influence the problem. But potential energy is very important. Okay, from problem to problem, and that is the thing that is going to vary. So it is the nature of the problem will determine the value of v. But at the end of the day, your basic job is to solve this equation. You put v, but you have to solve it. So what we did yesterday particularly, that is in our previous lecture, that we have converted this equation. This equation itself is a very typical equation. It's a differential equation or partial differentiation equation. Right hand side is non-zero, and it's a, so what we did actually, yes, last day we actually used a basic technique of mathematics known as the separation of variable to convert this equation in a very simple form. What I did, we considered that separation of variable tells us in this equation you write down psi as a product of two functions. One of them is space dependent, another is time dependent. After that, so what I am doing actually, I am writing down as a product of two functions. One is a function of x, the other is a function of t. So all the terms on the left, actually, those psi, d2 psi dx2, d psi dt, and the psi itself will be now replaced with this right hand side term. Okay, so basically what would happen, these are the replacement. If I do it, it converts from an equation in psi to equation in phi and f, as you could see. So ultimately, these are the steps that we have followed last day. Ultimately, we had an equation whose one side was depending on the space part only, other side was depending on the time part only. I told you it is very, very important deduction. Okay, yesterday also. We get an fallacy like this, an equation whose one side depends on x, other side depends on t. We initially thought that the equal sign can exist then if x and t are dependent of each other, but in our problem x means position, t means time. So only possibility is that the equal sign can exist is that both the term produces separately some constant quantity. Okay, these are some of the examples I told you. This is a basic idea that if it is any equation like that 5x squared d2 dx2 equal to ddt of 10t is possible, that if after derivative etc you end up with a constant. Here also one side of that equation, if you see at the top, okay, here at the top of the top, if you look at the top, you will notice here this portion is depending, the one part is depending on the time and the other entire part is depending on x. So basically so it is only possible that because here x and t are independent of each other, so it is only possible both sides of the equation are equal to each other. The equal sign can exist if both of them are producing, they do not end up with x or t dependent term, rather they end up with some constant term like that 10. Okay, I made a detailed, thorough discussion in previous class, if you recall. So ultimately, my equation takes a form like this. If both sides produces some constant, so ultimately my equation would be like this. For just a second. Okay, it was like this. It is again from the previous class. The equation in time is easily anybody can do it. Okay, it will be going to give you e to the power solution, and equation in space, equation in x is giving you some wonderful idea. It gives me an equation very similar to original equation of Schrodinger, but it is not keeping any time term. So equation is in x is popularly called time independent Schrodinger equation. So this little deduction, okay, starting from the previous page to this page, okay, that I have been doing. Last day I have made a thorough discussion, okay. I did it by on pen and paper. If you could recall, you can see that video for reference. So if you follow step by step, just a second. If you follow step by step, the idea is that idea is very simple, okay, that you have to only follow step by step, and you end up with an equation whose one side depends on x, other side depends on t. It is only possible if both sides are equal to constant, and I end up with a time independent version of the Schrodinger equation. So this conversion from time dependent, that is x, where Schrodinger equation involves both space and time, to the time independent equation is a very important reduction, and that final equation of Schrodinger will be utilized, okay, that will be solving problem, because you can see time part is easily solvable, okay. Main botheration, main concern will be on the space part, okay. So if we could solve that equation, when problems will be solving actual problem, as I mentioned, problem to problem v is going to vary, so our main botheration will be to get the function psi. Now question comes in, suppose you solve the equation in psi, you have solved Schrodinger equation, you have got a psi, what you do with this psi, because what you will get at the end of the day, you will end up with the function. Psi will be a function, mathematical function, and it is expected that if you solve the differential, take the smart square of psi, you will get the probability or chance of finding the particle. Now the question is that after knowing the psi, what else I can do, because only knowing the position does not mean the mechanics, okay. Mechanics of an object, suppose I have got a train moving or car moving, only knowing where the train is, that is not the full mechanics, okay. It can do many more things in the journey. I will show you some examples very soon. The idea is that if you have to describe the full mechanics of an object, full dynamics of the object, only knowing psi, and from psi knowing the mod psi square means the probable position of the object, is not going to develop the full of quantum mechanics, okay. So but you see, but without you at least had something in your pocket, the functional form of psi, if you solve Schrodinger equation. So now, as I was mentioning, that when we'll be solving some more realistic problem, okay, we'll be solving 3 problems as I mentioned as per your syllabus. Each problem at the end of the discussion will give me a function psi, and each problem solution means I will be doing a bit of mathematics. Now the question is that unless and until I use psi for the purpose of some more meaningful calculation, or for extraction of some more meaningful data related to the motion of the electron or any particle for that matter, then my entire discussion will almost become. So I have to put lot of physics into the discussion of psi. I have to make psi more meaningful. I have to do psi, and to do that we have to now deviate by our discussion a bit. So we'll solve Schrodinger equation, we'll be solving actual problem after some time, but let us do a magic with psi, okay. Let us do something more meaningful with psi. Let us see what we can do with psi. To do this little thing, what I am trying to tell you is that let us knock psi, let us talk with psi, okay. Let us do something with psi. For that purpose I ask you it's some basic question of mechanics, because it's all mechanics. It's mechanics but quantum mechanics but small particles, okay. So now question is that what do you mean by mechanics of an object, okay. I have presented you so many examples. Obviously these are not quantum mechanical example. I have got a body connected with a spring, you can see there, it is moving. I have got a particle moving in a circular path like this one. These are all mechanics problem. Now you can see, how do you know that the big mass is moving? Because as I am talking, it is changing its position, okay. So because it's changing its position with time, its position against the time, so it's a problem of motion, problem of dynamics. So because it is answering 2 of my basic mechanical question, that is where and when. Where that bob is, I am not sure. sure it is changing. I am not sure means that as the time is changing, its position is changing. So WH questions are answered. If I put a scale there, make a scale there also. Using my clock, I can get the time, and with time I can note down the position. So from there on, I can say as time changes, the bob is changing its position, the block is changing the position. So I've got a bob under motion. So it's a problem of mechanics, problem of dynamics. I'm giving you some more examples, then you will realize. If you look at this example, these are very good example. Okay, some more large objects are moving. Okay, suppose I have got a that bob is moving, and I have those two bodies are there. Okay, two bodies are there. One is indicated by the black color, one block. Another is indicated by the blue color. They are connected with two springs. They are moving. So if their motion is periodic motion, you can see some sort of curves are generated. Now, can you point out? Can you note down what are the difference between the two vibrations? You see, one of the curve, the black one is happening very smoothly, but the blue one have got its diminishing amplitude. Now this illustrates another important issue, that if I investigate the two motion, they are not happening similarly, because I am generating two different types of graphs. So one, the motion, the way the black colored block is moving connected with this black colored spring, and the way that blue colored spring block is moving connected with the blue colored spring, their motions are not similar. So if I only know the description of the bob and two blocks as that, as position time changes, their position changes, you see that is not going to decipher that why they are moving separately, why I am getting two different types of graph, because those curves are actually plotting the positions of the object against time. Positions are changing, their positions are different against time. But okay, fine, you may say positions are different against time, so I am giving two to a different type of motion, but that does not illustrate why they are moving differently. Answer, you know, okay, they are the concept of the damping forces due to spring, etc., responsible for that. So damping force means key. What I am trying to tell you to describe why the amplitude of the blue block is lesser than the amplitude of the black block, and why not the blue block. These questions are not answered if you know only the position of the object. You need more data. That is, the velocity is falling. That is, because amplitude is diminishing. So it's a problem of its damping motion. Okay. So I have got one more parameter added into my discussion apart from position to describe the mechanics of the object. That is the velocity. Obviously, other parameter that is involved, what is the force acting, because spring forces are involved. The more elastic spring has got higher spring forces. You know this, it is equal to minus kx times force for a spring. My objective is not to tell you the how spring vibrates. My objective is to tell you, if you have to describe the motion mechanics of the springs, you need lot of data. Okay. These are all classical examples, you know them. Some more example. Okay, suppose pendulums oscillating. Okay, again you see two pendulums, they are vibrating in dissimilar manner. Okay, their positions of the bobs are changing with, okay, all these things you can see. They are vibrating dissimilarly, means ki the forces they are experiencing are different. So apart from position, I need more data, like damping means it is connected with velocity. So more other data like velocity, like force are coming into the business. So with all these examples, you see these are all known examples. All of you know this. All these examples, whatever I am trying to help tell you, that mechanics does not mean only knowing the position. You need more data. Okay, that means in quantum mechanics also, only knowing psi and only knowing mod psi square, that is the probable position of the object, is not the mechanics of the object. You need more data, just like they are in the case of these trains. Okay, trains are moving. How do you know trains are moving? Because positions are changing. But you see, they are moving so many differently. Okay, a man is walking. Okay, now some more examples are the motion of the train. You see beautiful pictures of the train. What the trains are doing? Are they moving regularly? No, they are suffering accidents. They are colliding. Okay, the moment collision comes into business, you realize apart from the position and the velocity, etc., some more force, etc., some more data are coming into business. That is kinetic energy and potential energy, because for the collision, energy conservation is an issue if it is elastic collision, okay? And in elastic collision, energy not conserved, but the question of collision, energy, total energy before and after, all these things will be important. So what am I trying to tell you? A single pendulum, a block, or even a train can move in variety way of the way. Whether the train is moving or not, that will be exemplified by this picture. Okay, as you could see here. Whether the train is moving or not, that you can see here, as if it changes the space position with time. But during the journey, if it stops, if it moves fast, if it moves slow, some more data are coming into the business. Actually, those things predict where the train will go after some time. Okay, so that is like velocity, acceleration, momentum. They will come into business. These are more realistic. It may collide also. The other parameter like kinetic energy and potential energy comes into business. So the message is very clear that to describe this motion of a single train, you need so many data. Only position with time is not good enough. So idea is that motion of the train, motion of the bus, motion of the man, or even motion of the electron, all of them are at the end of the day are problems of motion, problems of mechanics. Okay, and any mechanics problem is therefore not just described by knowing just by position. You need a lot of other data. Okay, if you know all of them, then you can successfully describe the motion of the object. This is something you have to remember. Okay, I've been keeping on telling, but you have to remember, you have to realize, you have to understand that motion does not mean only knowing position with time. Position with time will tell you whether it is moving or not. But to do prediction that how it is moving, okay, you need lot of data. You just see this picture. Some blocks are falling. Okay, these blocks are falling down. So some bodies are falling down. It is another type of problem, too. Another type of motion. Somebody under friction. Okay, so another force comes into business. So if you have to describe this problem, you need more data. Okay, there is how it will move, when it will fall, the concept of frictional force, etc., will come. So to describe the motion, you need lot of data. Okay, like force is important here. Okay, there are few more examples. Suppose two bodies are colliding, all these things. Okay, you see collision is taking place. Energies are important, kinetic energy, potential energy, they become important. Okay, so these variables, so if you see, it may be a block falling, it may be a lot, they say 4 balls are falling and along a slope plane. Okay, along a slope. So lot of parameters are involved, they are falling, so positions are changing with time. So there are two variables. If they fall, their velocities are important. Some of them, because you see, as they fall, as they are falling, they are experiencing frictional forces. Okay, so forces are coming into business. Okay, so a lot of parameters are coming apart from position and time, like velocity, like momentum, like force. If collision takes place, energy, all these variables together therefore needs to be described motion of any object. It may be the motion of the car, it may be motion of the pendulum bob, it may be the vibration of the spring, or it may be the some bodies falling down. The more lot of data apart from position and time are involved. Only position and time falls on a slanted plane. So lot of other data like force, like velocity, like if you know all possible cases. So if it is true for a car, it's same thing is true for electron also. Like if it is moving inside an atom, which is a quantum mechanics problem, expect chi square is going to give you the probable position of the object. But what I'm trying to tell you, only just by knowing the position is not going to help. If I like force, like velocity, like acceleration, like momentum, all of them, all these variables together have got a name. They are called dynamical variables because they are associated with the dynamics of the object. Now the question is that for a car, for a bus, for a train, or if some body big objects are falling down a plane, you can calculate these dynamic variables very easily. You can get these dynamic variables very easily because those objects you can see. Newtonian techniques are known to you, and you know that calculate the force, you solve the equation, you calculate the position. All these things are known to you. Now, so the idea is a large object is large. If I use the simple Newton's law, if it's a big object moving, I know its mass, I know I see its how it is moving, I calculate its force, etc., etc. I can describe the motion. But the problem is that in a quantum mechanics class, I do not discuss about the car or bus or train. In quantum mechanics courses, we talk about the tiny electron. Just as you can see in the picture, electrons are moving. But my problem, I cannot see. I take chances to find out the electron. Chances are varying. So I define a wave, probability wave of the electron. Okay, and that is, or I define that the wave is defined by a mathematical function psi. So you see the matter is moving. Your parameter, you see psi is also changing. Okay, so the quantum picture is that I have got only one thing in my hand, but if electron moves, try to realize electron, if it is moving here, it is also associated with dynamic this type of variables. Okay, you see this picture. If you look at this picture that you see here, if electron moves also, I've got three electrons moving. Okay, you see defined by three different wave packets or three different wave function or three different the probability the waves or three different size, I should say. Okay, and they are moving differently. Okay, now to only knowing the, you see they are moving differently, how do you realize? That means by seeing I see, I'm saying they are moving differently. But the idea is key. Some of them are moving fast, some of them are moving slowly. That means the parameters of motion, apart from position and time, are important. Like momentum, like kinetic energy, like potential energy. But problem is that all of them are, again, as I mentioned, called dynamical variables. Problem is that how do you get them in this case for the electron problem? Okay, that is a problem. How do you get them? Because we cannot see the matter. How do you get them? Then what you have to do something so that object is moving. These are all mechanics problem. A car moving, a train moving, a bus moving, an electron moving, all are mechanics problem. So all of them need to be described by the measurement of dynamical variable. Question is that how do I get them? Function. Okay, described by some. I can plot them also. Okay, but to know where it is, in a real problem, I have to calculate. I have to try to calculate that. Okay, so we have to now adapt, and you can realize I cannot see the matter, so I cannot do the direct measurement also. Just like suppose this is a pen drive, I ask you where it is. If I throw the pen drive, okay, it will you see if how do I know that it is moving? It is moving like this. How do I know this pen is moving like this? Because I can see the matter is moving. Okay, but in electron I cannot see it. So I'm relying on psi. So now I can get psi by Schrodinger equation. But so that psi now can be exploited to get those additional information of motion. Okay, because the matter is moving. You know matter is moving. Your problem is you are not getting it. So but you know by solving Schrodinger equation you know psi. So we have to do something so that from psi we can extract the related information of motion. Okay, so how do I get it? Again, a lot of other examples are there also. The matters are moving, wave function is changing. I need to calculate the psi. Okay, I have solved the Schrodinger equation. I have got psi. So now I have to do something so that from psi I get the other dynamical variables information. Okay, I get all the other dynamical variables. Okay, all the other dynamical variables I can get it. So what is the technique? Technique is that suppose I get psi by solving Schrodinger equation. So from psi, I have to get all the parameters of motion. The idea is that as if psi knows everything. So as if psi is like a man. Psi knows everything. I have to attack psi. Psi, tell me the momentum. Psi, tell me the kinetic energy. Psi, tell me the potential energy. And psi will answer my question like this. So I have to talk with psi, and as if psi will tell me the answer. Because I've got no other option. Psi is it can be obtained from Schrodinger equation. I am talking about what you do with psi. So now what you do with psi, you can exploit psi. You can talk with psi. You can utilize psi to get those parameters of motion. Okay, you have to talk with psi. But problem is that I can talk with you in my human language, but psi is not a human being. Psi is a mathematical function. So if you have to talk with psi, you have to take the help of the help of whom? You see the list. Your mathematics teacher self you have to make, because psi is a mathematical function. So if you have to talk with a mathematical function, you have to talk with a function mathematically. And your mathematics teacher knows only 4 languages. Okay, that is the integration, differentiation, multiplication, subtraction, and all these are mathematical operation. The idea is that you do mathematical operation on Shai. Okay, you talk with Shai in the language of operator, and it is expected after talking, Shai is going to give me some data. Okay, so the answer is that to get the physical information other than position, what is my answer? Answer is that all information are stored in Shai. So I have to now knock Shai. I have to ask Shai, Shai, what is the momentum? Shai, what is the kinetic energy? Shai, what is the potential energy? Shai, where is the position or what is the object is situated? So I have to ask Shai so many questions, and Shai will be answering my question. What I am trying to tell you, Shai is a function of mathematics. So if you have to talk with Shai, you have to talking with Shai in the mathematical language. Okay, so that is something what we have to do, and that language is called the language of operators. Okay, these are beautiful pictures as you could see. Okay, now I have to introduce the idea of operators. The operators will be talking with Shai, and Shai will be answering the question to know the to give you the physical information. Okay, now to do so, what shall I do now? Actually, you have to learn a technique. Okay, of how to interact with Shai, how to talk with Shai, so that Shai can answer all your question. Okay, how interact with Shai. Okay, so, you interact with Shai through the ideas of mathematical operators. Okay, now let me do it by pen and paper, let me do it by hand, let us be get into the details of the mathematics. What is a little bit of extra mathematical idea you need to talk with Shai. Okay, so let us see that, let us do that. Just a second. Okay, just this technique. What shall I do now? Actually, I will first tell you one classical example. Okay, one example of two examples I am showing. You can see here. One is the example of a moving car. A car is moving. Car motion is obviously the example of a classical mechanics example. Okay. The first example I choose is classical mechanics, and the other example I choose is the example of a moving electron, and you can realize it is the example of a quantum mechanics. I'll actually tell you what is my information I told you with all those examples. Even if a car moving or even if an electron moving, your technique is that to describe if a car moves, what would happen along x direction, its position will keep on changing against time. If electron moves also along x direction, if its position x will change with time. But what I am trying to tell you, if car moves, it should have some momentum. Similarly, if electron moves also, it should have some momentum. If car moves, it should have some kinetic energy. If the electron moves also, it should have some kinetic energy. So the idea is that it may be an electronic motion, that is a microscopic object, or it may be a car motion. At the end of the day, both the problems are the problems of motion, problems of mechanics. And as I told you, any mechanics problem is described by knowing some variables, dynamical variables, not just position and time. Momentum, velocity, force, kinetic energy, potential energy. If I know all of them, I can tell I know the dynamics of the object. Now here I have taken two objects. One is a quantum object, electron, another is a classical object. Information is that whosoever is moving, tram, bus, train, electron, proton, neutron, to describe the motion, you have to get this data. So all of them, all those data together are called dynamical variables. Okay. All these together, data together, are called dynamical variables. All of them are together called dynamical variables. So what is the purpose of keeping dynamical variables? They are needed to describe. They are needed to describe any motion. They are needed to describe any motion. Okay, you have to measure dynamical variable. Okay, we need to measure. To describe any motion, we need to measure some dynamical variables. and this is a small list of the dynamical variables. You have to measure position. Fundamentally, you have to measure position of the object at a given point of time. Position, okay, at a given time. You have to know the kinetic energy of the object. You have to know the velocity or momentum of the object. You have to know the kinetic energy of the object. You have to know the potential energy of the object. Summation of kinetic and potential energy in classical mechanics is called Hamiltonian, the total energy, total mechanical energy, as you can see. Hamiltonian of the object. Okay. And there may be any other energy E also. If I know all of them, I can describe the problem. Now what shall I do? That if a car moves, these variables are there. If it variables are there. Car is a big object. I know the technique. Classical mechanics has told you how to get this data. That technique I will repeat. What I am trying to tell you, if electron moves also, these variables are there. But how do you get them? You've got only one information within your hand, that is psi. So prescription is that you talk with psi. Psi will give you the answer. Okay. Psi will be giving you the answer. So how psi responds? So what is the way of, I told you the word that you talk with psi in the language of Rupak psi. Rupak psi's language means in the mathematics language. Okay. Mathematical language means in the language of operator, differentiation, integration, multiplication, as I have shown you. So we have to adapt a technique of mathematics now. So that technique of talking with psi, that is what I am trying to tell you. So my plan is that first I am telling what is happening classically. What is your technique of getting this data in classical physics? Then I will slowly show you how the technique changes into quantum world. Okay, that will be easier for you to understand. Okay. So what you did in classical physics, first you represented some symbols to represent these variables. For position it is x. For one-dimensional problem, time t, momentum p. I have already used the kinetic energy t, potential energy v of x. It's a function of position. Hamiltonian is represented by the symbol h. Energy is represented by the symbol E. And in classical physics, to get any variable, suppose I wish to know what is the momentum of the car. So I was having a standard formula, mathematical formula to help me. For momentum, this has been my formula, mass into velocity like quantity. Okay. For kinetic energy, you are having a formula like this, half of m u square type of formula. So this has been your classical formula. Potential energy depends on the problem. If it is gravitational potential, you write down say mgx. Hamiltonian is a summation of kinetic and potential energy. So whatever you see there, and this energy is other than mechanical energy. So you have to. So this is other than mechanical energy. So what you have to do, you have to write down that in a real problem. Okay, this is other than mechanical. Okay. So now, and for position, you do not use a formula, and for time also, you write down t is equal to something by looking directly at your clock. So this is your classical symbol. Now, what you have to do? You have to do the same thing for quantum world. That is the case of moving electron. Electronic position, electron at time is what you can see. What is the electron momentum? What is electron kinetic energy? So technique is that who knows this data? Psi knows it. Our assumption is that psi knows every data, all the information. So your technique is that psi, you have to talk with psi. You have to talk with psi. Okay, that is my technique. So how do you talk in the language of operators? So all the variables, all these dynamical variables, whatever I have listed there, all these dynamical variables here, whatever I have listed here, all of the dynamical variables will be now represented as operators in quantum mechanics. They are represented as operators in quantum mechanics. Because every operator is a language of talking with psi. So as I told you, all the information are known to psi. You talk with psi. Psi is a function. You talk with psi in the mathematical language. Mathematical language means language of operators. You talk with psi in the language of mathematical operators. Okay. So you do it, okay? You talk with Shai in the mathematical language operator. So every variable there exists a mathematical operator. So now these are the operators I am talking about. So now come back to classical physics, the way I did, similar to that, how do you make use of this operator? So similar to classical physics, every operator has got every operator will be represented by a symbol. Okay. So now the symbol is that you see you have been living in classical physics. Okay. Now you are making a jump into quantum mechanics. Okay. So what you are doing, you are moving from big macroscopic world to large small microscopic world. So because you are making a jump, you go to the market, bring a cap for you, hat for you, and then you make a jump. Okay. So what you do, just to remind you, I have told you. So all the classical symbol, you put a cap over it. Okay. So if you put a cap over it, it becomes a quantum operator. So X will become X cap. T will become T cap. P will become P cap. Capital T will become capital T cap. V will become Vx cap because it is a function of X. H will become H cap. And E will become E cap. Okay, all the symbols, classical symbol with a cap makes a quantum operator. So classically, every operator was having a formula like momentum was mass into velocity, kinetic energy was a half of m(v) square like this. So quantum mechanically also every operator should come up with a standard mathematical formula. I request you to remember two things. Only remember position remains unchanged, time remains unchanged, and momentum is a differentiation operator del x. So if you have to ask question to Shai, it will be operating one first order differentiation operator. If you remember these two information, then remaining three you can do yourself. Whatever I am trying to tell you, say for example kinetic energy. Classical mechanics tells you that I show you here, okay. Where shall I show you? I show you here at that kinetic energy is classical mechanically is this much, half of m u square. So if classical mechanics tells you this is half of m u square, this is nothing but mu whole square by 2m. So this is according to classical physics, this is nothing but p square by 2m. So if you are doing the operators, you have to write, you can write down this as p cap square by 2m. Because you know p cap, which is minus h cap del x, so you can easily calculate this, okay? Because you know p cap is minus h cap del x, so you can easily put the value of p cap from here on. This is your p cap, and calculate the value of t cap. So how do you get it? I show you here separately. Say what you have to remember? T cap is basically p cap square by 2m. So what you have to know, you know from the previous page, p cap is minus h cap del x. So what you have to do, t cap will be equal to p cap into p cap by 2m. So t cap will be equal to p cap value you put here minus h cap del x, and you put this p cap also as minus h cap del x by 2m. So what it produces, t is equal to minus, you can see here minus minus, this minus and minus will together become plus, h cut will become h cut square, and there are two i's will become h cut square, i's will become minus 1 by 2m, and del x acting on del x. So you can realize this will be minus of h cut square by 2m d2 dx2. So this is the operator form of kinetic energy. So what you do, you put it here in the formula. Kinetic energy means minus h cut square by 2m d2 dx2. Potential energy, you see potential energy is this much. Okay, I show you potential energy if is a function of x. Potential energy, for example, potential energy Vx is equal to mgx. Now in operator form, you are converting this into Vx cap, so it will become mgx cap. Now x cap, x does not change. Okay, x become x cap, and it does not change the formula. I have told you a few minutes back. So obviously Vx cap, which is equal to mgx cap, it is equal to, because x cap does not change, it remains unchanged. So Vx cap is equal to Vx. So I can write down Vx is therefore equal to remain unchanged. Hamiltonian, this is the summation of T and V. Okay, so Hamiltonian, if this is your T, just go to the next page. This is your T and this is your V. Okay, so if you add these two, you get Hamiltonian. Hamiltonian will therefore be this much, H cap equal to T plus V. T is this much minus H cut square by 2m d2 dx2, and V is unchanged. So this is the expression of the Hamiltonian operator. So if you remember T, and you can T that only the formula of this P cap, you see everybody knows from school the kinetic energy is half mv square, that is P square by 2m, P square by 2m in operator form, P cap square by 2m, or P cap operator is this. So this much of multiplication you can do at your age, so you can calculate this T cap. That is what I am trying to tell you. And because x does not change itself, potential energy, which is a function of x, which is also does not changing. So, and if you add this T and V, you get the Hamiltonian. So you don't have to remember it. So Hamiltonian operator from this expression is therefore minus h cut square by 2m d2 dx2 plus Vx, and energy is slightly different operator. Energy operator is plus h cut del T. Okay, so this has been the list. So what I have done here, if you look at the sheet now, I have got two problems. One is a car problem, one is a electron problem. Both of them are dynamics problem. To describe the motion of the car, this is my classical approach. To describe the motion of the electron, this is my quantum approach. What is the change? All the variables of same variables I have to measure, but quantum mechanics means I knows it. So for every variable, I am defining one mathematical operator. Mathematical operator means that will talk with psi, that will define one operation. You remember two things only: position is unchanged, time is unchanged, and momentum is minus h cut del x. If you know momentum, everybody knows kinetic energy half mv square. So that is p square by 2m, as I have shown you, p square by 2m. And so you can do this much: T cap is equal to pp by 2m. You put the value of P, we get that is minus h cut square by 2m d2 dx2. Next time is potential energy, which is a function of x. So it's v, x is unchanged, v is also unchanged. And if you remember this, that T formula and V formula, you can remember that you can get H also, which is T plus V. Okay. So what I am trying to tell you, if you look at this list, okay, in this list, what you notice that you only have to remember X and T unchanged, and the formula of momentum operator. If you know these two, next will follow you, T, V, and H. Whatever that is the one that. I have to only know two information: position and time unchanged, momentum is minus h cut del Lx. So if I remember these two, I can calculate kinetic energy, okay, which is shown here, minus this is the value. Everybody knows kinetic energy is half mv square, and that is p square by 2m. If you replace the p value, and you get the value of kinetic energy. Potential energy x does not change, potential energy does not change also, and Hamiltonian is a summation of these two, so you get the expression. So if you remember the expression of P and X unchanged, you can get these two are you can easily get, you don't have to remember at all. And difference is that energy operator is a time dependent operator. Okay, so these are the expressions, these are the forms of the various quantum operators. Okay, so if you look at the situation, If I now have an electron moving, and I suppose I solve Schrodinger equation, I know the psi, and I wish to get the momentum of the electron. So in which language I shall talk with psi, that language is there, minus h called del Lx. That means if I have to know the psi, if I have to know the momentum, I have to do the first order derivative of psi to get momentum. If you have to know kinetic energy, that is given here, like minus psi is representing the matter is in quantum mechanics. How do you talk with psi? If you have to know the momentum, operator of momentum will act on psi. If you have to know kinetic energy, operator of kinetic energy will act on psi. If you have to know the, so these are the operators. If I have to know the potential energy, operator of potential energy will act on psi. So the idea is that and these are the forms. Knowing momentum means you do a first derivative of psi. Knowing kinetic energy means you do a second derivative of psi. Knowing potential energy means you do to operate V on psi. Okay. Knowing Hamiltonian means you operate this operator on psi. So then psi is expected to give us the answer. Now what is the answer of psi to these questions raised here? If you ask, so if you have to know kinetic energy, this is the question to be asked to psi. A first question means a second derivative of psi. Now what is the psi's answer to give you the kinetic energy of the object? What is psi's answer to give you the momentum of the object, because momentum is the first order derivative operator. Okay, so what is psi going to answer? That answer I will tell you in the next class. Okay, and that heading is called actual measurement. So if you compare classically, you only know the formula of say half mass into velocity if you have to get momentum. But in a real problem, you have to put correct m and correct u to get the value of actual numeric momentum. So here also this minus h cut square by 2m dt dx is the formula of getting kinetic energy. So how do you get exact kinetic energy actually in a real problem? Okay, that is called actual measurement in quantum mechanics, that I shall highlight in the next class. Thank you for the time being. Thanks for your patient hearing. Okay, let us meet in the next day.